Hello everyone, we're back with another video of Solid Earth. Today we're going to be talking about the layers of the Earth, rock types and formations, types of plate tectonics, boundaries, continental drift, and margins. We're going to jump right into the layers of the Earth. The layers are classified in two ways, the chemical composition and the physical properties. If you look at the picture on the side, you can see that the chemical divisions are on the left and the physical divisions on the right. The first layer is the crust. It is the outermost layer of the Earth, like eggshells of a hard-boiled egg. Like the shell, it's broken into pieces known as tectonic plate. The crust can be classified as either continental crust or oceanic crust. Depending on what they are, the thickness also varies. Next, we're going to go into the mantle. The mantle is the thickest layer of the Earth, and it is the layer right beneath the crust, and it circulates really slowly. The outer core is the next part. It's what you see in this orange right here. It's made up of mostly iron and nickel, and it's heated by radioactive decay of thorium and uranium in the currents. And it is also responsible for generating the Earth's magnetic core. The inner core is the central layer, as you can see with this triangle, and you can think of it like a solid metal ball. It's extremely dense and heavy, and it's almost as hot as the sun. So we have the mechanical and physical divisions. As you can tell from the picture, we have the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. The outer core and inner cores of both the chemical and physical properties are the same. So we're going to jump straight into the mantle. As you can tell, it's composed of the asthenosphere and the mesosphere. And how do we distinguish these two is by their physical properties. While the mesosphere is rigid, hard material, the asthenosphere is plastic and it moves around easier. And then the lithosphere composes of the rigid crusts on top. Next, we're going to talk about sedimentary rocks. They're formed from pre-existing rocks or pieces of once living organisms. Some examples you may know: sandstone, limestone, and shale. Sedimentary rocks form from deposits that accumulate on the Earth's surface. These rocks often start as sediments carried into rivers and then are deposited into lakes and oceans. When buried, these sediments lose water and become cemented to form rock. So the most common types of sedimentary rocks are clastic sedimentary rocks. They have particles that range in size from microscopic clay to huge boulders. So we name them based on their classed size or grain size. The smallest grains are called clay, then silt, then sand. Grains larger than 2 millimeters are called pebbles. For example, shale is a rock made of mostly clay, siltstone is made up of silt-sized grains, and sandstone is made up of sand-sized clasts, and conglomerate is made of pebbles surrounded by a matrix of sand or mud. And finally, we have biologic sedimentary rocks that form when living things die. Next, we have igneous rocks. The word igneous comes from the Latin word for fire. They form when hot, molten rock crystallizes and solidifies. This usually happens within the Earth, near the active plate boundaries or hotspots, then comes towards the surface. We divide igneous rocks into two groups, intrusive or extrusive, depending on where the molten rock solidifies. Intrusive igneous rocks, or plutonic igneous rocks, form when magma is trapped deep inside the Earth. Some of the magma may come onto the Earth's surface, but most remains trapped below the Earth's surface, where it cools very, very slowly over thousands and millions of years until it solidifies. This slow cooling means that the individual mineral particles and grains have a very long time to grow. So they grow to a relatively large size, which produces the coarse grain textures that we know. You can look at the picture on the top right and you can tell which ones are the coarse grains and which ones are the fine grains. So the fine-grained rocks are extrusive igneous rocks. The magma, which is called lava when molten rock erupts on the surface, cools and solidifies almost instantly when it's exposed to the cool temperatures of the atmosphere. This quick cooling means that mineral crystals don't have much time to grow, so these rocks have a very fine-grained or even glassy texture. Sometimes hot gas bubbles are trapped inside the lava, which forms a bubbly, vesicular texture. You may know pumice, which is a type of igneous rock, and has lots of bubbles inside. Next, we have metamorphic rocks. Metamorphic rocks start out as some other type of rock. The process of metamorphism does not melt the rocks, but instead transforms them into denser, more compact rocks. This commonly happens deep inside the Earth where tectonic plates meet. New minerals are created either by rearrangement of mineral components or by reactions with fluids that enter the rocks. Pressure or temperature can even change previously metamorphosed rocks into new types. Metamorphic rocks are often squished, smeared, and folded. So, we have two types of metamorphic rocks, foliated and non-foliated metamorphic rocks. You can tell this by the way they appear. Foliated means the parallel arrangement of certain mineral grains that gives the rock a striped appearance. They're usually flaky and have sheet-like structures that reflects the way the pressure was applied to the rocks. Non-foliated rocks are ones that don't have the sheet-like structure. There are several ways that they can be produced. Some rocks are made of minerals that were not flat or elongate. So no matter how much pressure you apply to them, the grains will not align and it will stay coarse. Let's talk about convergent plate boundaries. This is when two tectonic plates collide with each other. We have three different types of convergent plate boundaries: oceanic-oceanic, oceanic-continental, or continental-continental. So for oceanic-oceanic, this happens when two oceanic plates converge and creates a trench. This is because oceanic plates are denser than continental plates, and as a result, they naturally subduct or go underneath into the mantle. Oceanic-continental convergent plate boundaries is when a continental and an oceanic plate converge. The oceanic plate always subducts underneath the continental, which creates volcanoes, active margins, and trenches. Finally, we have continental-continental convergent plate boundaries. This is when two continental plates converge and the plate is pushed upwards, which creates a mountain range. Next, we have divergent plate boundaries. We have two types of divergent plate boundaries. We have continental divergent and oceanic divergent. Continental divergent plates are divergent boundaries over two continental plates, which causes rifting, in which the continental lithosphere, or the crust, stretches and breaks apart, which is where seafloor spreading begins. For example, we know the African Rift Valley, which is a prominent example of a continental divergent boundary, and it's currently splitting the African plate into two plates, the Somali plate and the Nubian plate. We also have oceanic-oceanic divergent plates, where two oceanic plates diverge to form a mid-ocean ridge. At these boundaries, seafloor spreading occurs as plates spread apart and new oceanic lithosphere comes in between. For example, you may know the Mid-Atlantic Ridge. For both of these divergent plate boundaries, you could tell where it starts because the newer rock is always in the center, and as you go outwards from the boundaries, the rock gets older and older. Next, we have transform plate boundaries. Transform plate boundaries are when two plates slide past each other. No old plate is subducted and no new plate is formed at the transform boundaries. They simply slide across each other. This is usually marked with faults and a lot of earthquake activity. You may know the San Andreas Fault, which is the most famous fault that occurs along a transform boundary. Next, we're going to talk about the history of plate tectonics. It all starts in 1912 with Alfred Wegener, who composed the theory of plate tectonics. Wegener believed that about 250 to 300 million years ago, there was a supercontinent named Pangaea, which slowly split apart to the current positions we see today. This is also known as the continental drift theory. He also suggested that the continental coastlines on the opposite sides of the Atlantic Ocean could fit together like jigsaw puzzle pieces, and found similar plant and animal fossils around the oceans. While this made sense from a practical point of view, Wegener didn't have a geological way to prove this was true. After looking at various pieces of evidence such as fossil patterns, mountains, he came up with a geological theory that the Earth was made up of plates that moved around, thanks to the rotation of the Earth, which caused Pangaea to split up. However, he was later discredited for a lack of an explanation. In 1929, Arthur Holmes came up with a way to explain plate tectonics through mantle convection. He thought it would cause the plates to move around the Earth under a bed of mantle convection belts. This idea, however, was not paid attention to until the 1960s, when scientists discovered a geomagnetic anomaly around the ocean floor near trenches and the existence of island arcs near continental margins, which suggests the possibility of convection. These pieces of evidence led Harry Hess in 1962 and Robert Dietzen in 1961 to publish independently a theory known as seafloor spreading, which now is the main way to explain why plate tectonics exist. In 1863, Frederick J. Vine, Drummond H. Matthews, and Lawrence W. Morley suggested that the new crust would have a magnetization aligned with Earth's geomagnetic field. Over time, this would appear as bands of crusts that exhibit alternating patterns of magnetic polarity. This further provided more evidence that Earth's plates separated in mid-ocean ridges. In 1968, the vessel Glomar Challenger collected core samples from drilling holes in the overlying sediments and into the oceanic crust. This revealed that rocks closer to the deep ocean ridges are younger than rocks farther away from the ridges, as we talked about. This was later called the deep sea drilling project. Now we're going to talk about margins. There are 4 types of plate margins: constructive, destructive, conservative, and collision. Constructive margin, as you can see in the top right, is when 2 plates move apart. They form ocean ridges and volcanic islands. A destructive margin is where an oceanic and a continental plate meet. They form mountains and ocean trenches. A conservative margin is when 2 plates slide past each other. And a collision margin is when 2 plates move towards each other. So, in summary, we have the layers of the Earth are divided into 2 categories: chemical and physical divisions. We have 3 types of rocks: sedimentary, igneous, and metamorphic. Sedimentary rocks are made from compact deposited particles. These particles can range in size from clay to silt to sand to pebbles. We have igneous rocks that are formed from cooled magma. And there are 2 types of igneous rocks: extrusive and intrusive, depending on where and when and how they cool. Metamorphic rocks form from heated and compressed rocks, and they are categorized into 2 types as well: foliated and non-foliated. You can tell if they are foliated by their sheet-like structure. Anything else is non-foliated. There are 3 types of plate boundaries: convergent, divergent, and transform. Convergent plate boundaries are when 2 tectonic plates come together. Divergent are when they drift apart, and transform is when they slide past each other. The continental drift theory states that all of the continents used to be part of one supercontinent named Pangaea. Over time, they split into the continents we know today. The theory of tectonic plates is supported by the seafloor spreading in mid-ocean ridges. This proves that tectonic plates move and form new rock. There are 4 types of plate margins: constructive, destructive, conservative, and collision. In our next video, we're going to talk about major volcanic eruptions in history, as well as the major tsunamis, earthquakes, natural disaster responses, and mountains. See you then.